In this video, I'll discuss the idea of an equilibrium potential. Before defining an equilibrium potential, we need to first discuss the idea of a membrane potential. In both cases, the term potential refers to a voltage. A membrane potential is a voltage difference between the inside of a cell compared to the solution around the cell. In this diagram, we have a cell in solution. We can record a voltage difference between the inside of the cell and the outside using a glass micropipette and a special type of voltage meter called an intracellular amplifier. The membrane potential is referred to as V sub m. If the cell is resting, meaning that it's not generating an action potential, then the membrane potential is called the resting membrane potential. The resting membrane potential of a cell is called V sub rest. All living cells have a resting membrane potential, and this potential is always negative. The value can vary between different types of cells. For example, cells within your brain called glial cells typically have a resting membrane potential of about negative 90 millivolts. As I said at the start of this video, we will discuss the idea of an equilibrium potential. Understanding this concept will help us to eventually understand how cells generate a stable resting membrane potential. To understand the idea of an equilibrium potential, we need to talk about the unequal distribution of ions across the membrane of a cell. In all the cells in your body, there is a higher concentration of potassium ions inside compared to outside. This unequal distribution of potassium ions is due to the action of the sodium-potassium pump. Sodium-potassium ATPase pumps potassium ions into cells. At the same time, it pumps sodium in the opposite direction out of cells. As a consequence, there's a higher concentration of sodium outside compared to inside. For now, we'll concentrate on the effects of the unequal distribution of potassium. Cells in your body are complicated. For this reason, we'll consider an artificial cell with a membrane that is permeable to only potassium. This means that potassium can move freely between the inside and outside of the cell. Other ions, such as sodium and chloride, cannot. Let's imagine that there's a higher concentration of potassium chloride inside of a cell compared to outside. In solution, the potassium chloride salt dissociates into potassium ions, which are positively charged, and chloride ions, which are negatively charged. In this diagram, the potassium ions are shown as red squares, and chloride ions are shown as purple circles. Recall that there is a higher concentration of potassium ions inside of the cell compared to outside. Therefore, potassium ions will move down their concentration gradient from inside of the cell to outside. For each potassium ion that moves down its concentration gradient, there will be a net gain of one positive charge outside of the cell, and there will be a net gain of one negative charge inside of the cell. Why is there a net gain of a negative charge inside of the cell? Well, remember that the potassium and chloride were previously paired 1 for 1. Now, however, there is an unpaired chloride ion inside of the cell and an unpaired potassium ion outside of the cell. Of course, it's not just a single potassium ion that moves, but many potassium ions that move. Over time, a difference in voltage arises between the inside of the cell and the outside. The inside of the cell becomes negative with respect to the outside. As the inside of the cell becomes more and more negative with respect to the outside, there is an opposing force that will slow down and eventually stop the net movement of potassium ions out of the cell. To understand this opposing force, let's look at the distribution of positive and negative ions after a period of time in which the potassium ions are allowed to move freely across the membrane. Notice that there's a buildup of excess positive charges on the outside of the cell. Simultaneously, there's an increase in the number of negative charges on the inside of the cell. Due to the movement of potassium ions, there is now a net negative charge inside of the cell compared to the outside. Furthermore, the positive and negative ions remain close to the cell membrane because they're attracted to one another. The electrical field across the membrane tends to attract positive ions into the cell. Potassium ions are positive, therefore they are attracted to the inside of the cell. On the other hand, the concentration difference in potassium will tend to cause the movement of potassium ions out of the cell. Eventually, as the potassium ions leave the cell and the electrical field across the membrane becomes stronger, an equilibrium is reached in which the effect of the concentration gradient is perfectly matched by the effect of the electrical field across the membrane. The voltage that causes an inward movement of potassium ions that matches the outward movement of potassium ions is called the potassium equilibrium potential. Notice that an equilibrium potential is defined for a specific ion. For example, here we have described the idea of an equilibrium potential for potassium. We could imagine alternatively that an artificial cell has only chloride channels. With such a cell, the equilibrium potential would be based on the distribution of chloride ions across the cell membrane. To summarize what we have discussed, if a membrane is permeable to an ion and there is a concentration difference, the ion will move down its concentration gradient. As the electrical field becomes stronger, a state of equilibrium is reached, in which there is no further net movement of the ion. The voltage difference across a membrane that perfectly counteracts a concentration gradient is called the equilibrium potential. It is important to note that there is a common misconception that the movement of a large number of ions is necessary for the generation of an electrical field across a membrane. In fact, the number of ions that move across the membrane to establish an electrical field is very small compared to the total number of ions in the bulk solution on either side of the membrane. Since the number of ions that move across the membrane is so small compared to the total number of ions in the bulk solution, it's possible to simply ignore their movement when doing calculations of concentration. For example, if we start with a potassium concentration that is 10 times higher inside of a cell compared to outside, then even after the movement of some of the potassium ions from the inside to the outside, resulting in the generation of an electrical gradient, the concentration of potassium inside of the cell would still be approximately 10 times greater than the concentration outside. As I stated earlier, real cells are complex. In general, real cells have cell membranes that are permeable to more than just one type of ion. However, we can ask the question, is it possible to determine the resting membrane potential of an artificial cell that is as simple as the one we've been discussing, one that is a membrane that is only permeable to one type of ion? It turns out that for such a simple cell, the resting membrane potential is equal to the equilibrium potential. The value of the equilibrium potential can be calculated based on the intracellular and extracellular concentrations of potassium in this case, using an equation called the Nernst equation. We will leave the discussion of the Nernst equation for another video. Thanks for watching.